All right. So we will again. This is from one of the reference books that we have. Okay, it's an ecological model. Actually, this I like this example because it really illustrates how interdisciplinary control theory is. Okay, once you know how you can actually generate mathematical models of systems, and you learn mathematical methods of modifying these systems, controlling these systems, actually you can apply them anywhere. Okay, not only in electrical engineering, but in many different disciplines, and that makes control systems knowledge a really powerful tool that can be applied in whatever field you're interested in. Okay. So again, this one clearly shows how domain knowledge actually is transformed into a mathematical model. Okay, and it's from it is actually from an influential text by Volterra. Volterra is known for nonlinear models, especially you will come across something known as Volterra series. These are nonlinear polynomial models, functions that can be used in many areas of functional approximation. Okay, so this is based on the classic article by V. Volterra. It is known, the name of the article is Variations and Fluctuations of the number of individuals in animal species living together. This article was published in 1928. Okay. This model is known in short as predator-prey equations. Predator-prey equations or model. But you will see that it's not limited to the predator-prey case. So do you guys know the meaning of a predator and a prey? Predator is like an animal that eats other animals, and prey is the animal that is usually eaten. Okay, so examples of predators are like lions and etc. Preys are like sheep, domestic animals and stuff like that. Okay, now this article actually created a new field in science. Okay, so this created the field known as population dynamics. And if you're curious, this kind of models are applied everywhere, from politics to economics and stuff like that. Okay, it's a very representative example. Okay, so let's take a look at what we have here. So we have two animal species involved. Animal species these are living together essentially. Okay, with populations. That means number of members indicated by n1 of t, n2 of t. So N1 of T is the population count of the first species, and N2 of T is the population count of the second species. Okay, so these are living together and interacting between them. Now, the species have birth rates. Birth rate of species is constant, specific to each species, okay, lambda 1 and lambda 2, okay. So obviously birth rate means this is per individual, okay. So that means if you have a 10% birth rate, that means every individual actually generates 0.1 individual, okay. So if you have a population of N1, that means you will have newborns, new individuals that are amounting to lambda 1 times N1, okay. So means an inflow of members, we call this an inflow of members that are equal to N1 times, lambda 1 times N1. I don't know why this is not going away. Hold on. So my here we go. Lambda 1 times N1 and lambda 2 times N2 for the two species. Okay? So lambda 1 and lambda 2 are two parameters of this model related with how new individuals are added to the population. We also have mortality rates. Mortality rates of species is a bit more complicated. And we will consider two different cases, okay? But this is related with the outflow of individuals, okay? With birth, you have new members coming into the ensemble, and with death, you have an outflow of individuals from the population, okay? So the mortality rate, this is supposed to be end, but I'm sorry, this mortality rate depend on the availability of the food, okay, as well as the risk of being eaten, okay. So because we will also consider one species actually feeding on the other species, mortality is also affected by the risk of being eaten, okay. In general, so we can write in general an equation, mortality rate for species 1, so mu I is the mortality rate for species I, that is equal to in general it's a function of the population counts. We don't know what kind of a function this is, but we will consider two different cases where this function will take two different forms. The death rate of the second population is another function. of n1 of t n2 of t. For the time being, we are just saying that these rates are functions of the number of members in the population. So if we have... Yes.
Sorry, do N1 and N2 species have prey and predator relationship?
Not right? Yet. Not yet. We haven't established that yet. We will consider two cases. In one of the cases, one of the species will be the predator and the other will be prey. But in the first case, we will have a different model, essentially. Okay? So this is more general than predator-prey. What kind of functions you put here determines who is predator, who is prey, and whether or not there is such a relationship between the members. So hence, the outflow of members, is given by species 1. We have an outflow of members that are the rate n1 of t, n2 of t, times the population count for the first species. And for the species 2, same, right? We have mu2 n1 of t, n2 of t, times n2 of t. Mind you, this means that this is a function, right? This is a function of n1 and n2. Okay? We haven't specified the function yet. Now, at this point, we will write down the main equation that will generate the differential equations for us. And this is given by a general principle that is known as the conservation law. Conservation law. Now, you know that, for example, the same kind of conservation law, arkadaşlar yazdığım henüz size ulaşmadı gibi görüyorum. Beni duyabiliyor musunuz?
Duyuyoruz hocam.
Tamam.
Kesiliyor hocam bazen.
Okay, I'm sorry about that. Let me see my... Okay. Now, conservation laws are at the core of many mathematical models. For example, in the case of circuit theory, conservation law generates the Kirchhoff's current law, right? The conservation of charge means that the amount of charges coming into a node has to be equal to the amount of charges going out. That means we have the conservation of charge, and that leads to the fundamental law, which is the Kirchhoff's current law. Okay? Same with Kirchhoff's voltage law. It's essentially coming from a conservation law. Here, the conservation law basically says that the members can come in and go out, but the difference has to be equal to the accumulation of members. So there is an accumulation. If the inflow is not equal to the outflow, there will have to be some kind of an accumulation, like charges being accumulated in a capacitor. So we have the conservation law saying inflow minus outflow has to be equal to the accumulation. Okay? Any questions so far? Now we will transform this fundamental relationship into a differential equations. From the conservation law, we end up with two differential equations. Let's write them down. Basically, inflow minus outflow is equal to the accumulation, means the change in the population count for the first species. This is the accumulation, right? Change in N1 has to be equal to the inflow, which is lambda 1 times N1. So I will take N1 to the outside of the parenthesis, minus the outflow, which is mu1 N1 of T N2 of T, right, times N1 of T. Okay, so the inflow is lambda 1 times N1 of T, and the outflow is mu1 N1 N2, a function of N1 and N2, times N1 of T. And the second equation for the second species, dN2 of T over dt. Similarly, we have lambda 2 minus mu2 N1 of T, N2 of T, times, do I have an extra parenthesis, N1, N2, yes, times N2 of T. So what does this look like to you from 302? What kind of a model is this? Is it a transfer function? It's a state space model, right? It's not a second order single differential equation. It's two differential equations coupled together. Both of them are first order differential equations, right? So this is essentially derives us to a state space formulation. Okay. So two different cases from biology that we will look at. Two different cases from biology on how we can define the two functions mu I is equal to mu I N1 and 2. Okay, so the actual model really depends on how we define these two functions. So we will take a look at two cases. Case 1. Both species compete for the same food. So they are not feeding on each other, so it's not a predator-prey relationship, but the species compete for the same food. So a simple model, again, suggests a linear dependence on the total population. Suggests a linear dependence on the total population. Because they are competing for the same food, their total population determines how much food remains. So we have a model, something like this, right? Total number of members of both species essentially determines availability of food, availability of food, and that in turn determines mortality rate. Is the logical flow of the model. So what it's going to be mathematically, we will write down a model like this. We will say mu I n1 n2 will be equal to a basic mortality rate gamma I plus a function of the total population. So delta I n1 plus n2, where we have both delta I a positive number and gamma I another positive number. Okay, I 1 2. What does this say? This say that independent of the food, there is a certain mortality rate, gamma I over here, but that is supplemented by deaths that are a function of how much members there is in the population. Why? Because more members means less food, less food means more deaths. So that is determined by this function. Okay, so we will consider this model. So with this, our model becomes d over dt n1 of t is equal to, if I congregate some numbers over here, so I will have lambda 1 minus gamma 1 times n1 of t minus delta 1 of n1 of t plus n2 of t times n1 of t. That is our first equation. And the second equation is very similar. That's going to be lambda 2 minus gamma 2 n1 of t minus lambda 2 n1 of t plus n2 of t times n2 of t is our model. Obviously, our model has some parameters that we don't know yet. We don't know what lambda 1 is, what gamma 1 is, lambda 2 is, gamma 2 is, and what delta function is. Okay? But this is, again, in nonlinear, a set of two first order nonlinear differential equations. So it's a state space model, but it's a nonlinear state space model.
Hocam,
Yes.
gamma türe bağlı mortality rate miydi? Orayı kaçırdım.
Şöyle, şuraya bakarsanız eğer, şu ilk denkleme şunu söylüyor. Mortality rate is a function of n1 and n2, but is composed of a basic constant mortality rate, gamma I, obviously for a species, so gamma 1 and gamma 2 might be different, plus a mortality rate that is a function of how many total members there are in the population.
Anladım, tamam.
Okay? So there is a fixed component and there is a component that is a function of what's going on in the environment.
Anladım.
That means even there is infinite amount of food, people will still die. Okay? So there is a fixed rate, but if there is no food, more people will die. Okay?
Lifetime expectancy gibi bir şey yani gamma.
Yes.
Daha da ondan ötürü.
Yes.
Yani.
Okay?
Hocam denklemdeki n1 of t, n2 of t olmayacak mı?
Nerede? Yes, there is a mistake here. Here, right? Let's correct that. Here, there is a correction. This is n2 of t. Okay?
Hocam nonlinearity şu delta term'ü katıyor değil mi?
Nonlinearity'yi burada şey katıyor tabii ki. Yani delta is a function of n1 and n2 but is also multiplied by n1. Yani şuradaki product aslında sebep oluyor ama tabii ki delta 1 fonksiyonunun yapısı da buna sebep olabilir. O yapıyı da bilmiyoruz şu anda. Yani delta 1 de lineer mi değil mi onu da bilmiyoruz. Okay?
Ben de bir şey sorabilir miyim?
Yes.
N1 ve N2 burada aynı besinle beslenen farklı türler gibi bir şey mi?
N1 and N2 evet burada aynı besinle beslenen iki farklı tür gibi. Yani aynen öyle.
Tamam hocam, teşekkür ederim.
Okay. So let me tell you, in fact you can simulate this, but let me give you some idea about how this model behaves. Okay. I mean you can use MATLAB to play around with this model easily. It can be shown for example through simulations or theoretical analysis that I'm not gonna go into, okay, that if this relationship holds, and I'm gonna show you what this relationship means numerically in a minute, lambda 1 minus gamma 1 over delta 1, if this ratio is larger than, lambda 2 minus gamma 2 over delta 2. Bu arada arkadaşlar bir şey yanlış söyledik. Onu düzeltmek istiyorum. Burada bu bir fonksiyon değil. Delta bir fonksiyon değil. Delta bir constant. Özür diliyorum. Bir an dikkatim dağıldı. Dolayısıyla burada nonlinearity bu delta'dan gelmiyor. Delta burada bir constant. Ama n1 artı n2'yi n1 ile çarpıyor olmaktan geliyor nonlinearity. Çünkü n1 kare artı n1 n2 gibi bir terim geliyor burada. O da nonlinear bir ifade. Dolayısıyla burada delta 1 ve delta 2 popülasyonlara ait birer constant parametre olmuş oluyor. Yani ne parametresi bu? Popülasyon sayısının ölümü nasıl etkilediği ile ilgili bir sayı. Burada da aynı şey söz konusu. Tamam. Soru var mı? So it can be shown that if the first ratio is larger than the second ratio, in fact, the second species, in this case, the second species will die out, and the first species will approach a population count that is lambda 1 minus gamma 1 over delta 1 independent of the initial populations. Okay, that is quite surprising because it basically says even if the first species is abundant in the environment, very large number, and there is a very small number of the second species. Just the reverse, right? There is a large number of second species, and the first species is with a very small number, but this relationship holds. That means the second species will die out, and the first species will become the only species in the population. Okay, so let me give you some simulation example. Simulate, and you can do this in MATLAB. Simulate this system for these parameters. Let's say lambda 1 is equal to 3, lambda 2 is equal to 2, and gamma 1 equals gamma 2 equals delta 1 equals delta 2 equals 1. So what does this say? That lambda 1 is just larger than lambda 2. All the other things are equal. What is lambda 1? Let's take a look. Lambda 1 is the birth rate, right? Is the birth rate of the first species, and lambda 2 is the birth rate of the second species. So everything else is the same, but the first species birth rate is somewhat larger. Okay, so let's check the condition, whether we have this condition apparent. Okay, so I have lambda 1 minus gamma 1 over delta 1 is simply equals to 3 minus 1 over 1. So it's equal to 2. Is it larger than the second lambda 2 minus gamma 2 over delta 2? So obviously this is 2 minus 1 over 1 is equal to 1. Okay, so because 2 is larger than 1, so we expect that the first species will prevail. Okay, so 2 larger than 1. So we expect the first species to prevail. So if you simulate this with some initial conditions, I will give you just a quick sketch, and you can verify this in MATLAB if you want. So let's say N1 is with a very small population initially, but N2 is with a very large population, N2 of 0 here. Okay, so what's going to happen is that there will be a final value, and the first species will basically increase and will approach this final population. But the second species, independent of how large its initial population, it's going to simply, have a certain behavior and will die out to 0. In fact, it's going to go directly to 0, okay? It's not going to approach 0, but it's going to become 0 after a while. Or maybe it's going to approach 0. Yes?
Bu nonlinearity'de kafam takıldı da bu iki değişkenli olarak linear bir equation olması için iki değişkenin de birbiriyle çarpılmaması falan gerekiyor değil mi? Ayrı ayrı constantlarla ya da kendi kareleriyle falan olmalı.
Şöyle, yani şunu hatırlayalım. State space'te lineer bir sistem nasıl yazılıyordu? Yani şöyle yazılmıyor muydu? Mesela state space linear system. Gene iki değişkenli yazacağım. x1 dot is equal to şöyle olması gerekmiyor mu? x1 dot x2 dot şöyle yazayım bir saniye. Matris şeklinde yazayım gene. Bir kere mutlaka şöyle olması gerekiyor. Burada bir A matrisi olması gerekiyor. Ve bunun constant olması gerekiyor. Değil mi? Constant olması gerekmiyor aslında. Time varying de olabilir ama içinde hiçbir state olmaması gerekiyor. Or function of time. Zamanın fonksiyonu olabilir. Ama içinde x1, x2'den hiçbir şey olmaması lazım. Yani dolayısıyla şöyle düşünün. Mesela constant coefficient olduğunu düşünelim. Yani o ne diyelim? Time independence ile ilgili bir şey. Yani constant olursa time independent olmuş oluyor. Eğer zamanın bir fonksiyonu olursa time varying bir sistem olmuş oluyor. Doğru mu?
Anladım şimdi hocam.
Yani dolayısıyla bunu açarsam mesela şöyle oluyor. x1 dot equals to buna a11, a12 diyelim. a11 times x1 plus a12 times x2 olmuş oluyor. Değil mi? Şey yok. Bu a11'ın içinde artık x1 veya x2 olamaz yani. Ama şöyle olabilir. Time varying örneğinde şöyle de olabilir. Or a11 of t times x1 of t plus a12 of t times x2 of t de olabilir. Bu da time varying olmuş oluyor. Time varying. İleride 501 mesela 501 dersinde hani time invariant ve time varying örneklerle karşılaşacaksınız. Okay? Buradaki ilginç şey bu örnekte note the very small initial population for x1 of x1 nereden çıktı? N1 of t. Yani ne kadar küçük olursa olsun N1 giderek büyüyüp belli bir yerde satüre oluyor anlamına geliyor. Okay?
Hocam benim bir sorum var.
Yes.
Hocam ben delta'nın tam olarak neyi tanımladığını anlamadım.
Neyi tanımladığını anlayamadınız?
Delta'nın tam olarak nasıl bir constant olduğunu yani neyi belirleyen
Okay.
bir constant.
So what is delta? So in this model, right? In this equation over here, this is the death rate. Okay? So it determines how people or population members die. What it says is that this death rate is a constant, which is a constant death rate independent of the resources, plus a coefficient times the total number of members in the population. Okay, so this relationship shows that with a parameter delta, more members in the environment means more death rate, okay, for each species. How much so is determined by delta. Anlatabildim mi?
Evet hocam teşekkür
Okay.
ediyorum.
So let me move on to the second case, okay, which is also very interesting. Case 2 is now the case of predator and prey case. Okay. So what's the assumption? The assumption is that the first species feeds on the second species. Okay. Now, assume that first species feed on the second species. Now, the death rate becomes very interesting in this case. Feeding means obviously eats the second species. Okay. Now, what is interesting here is that the supply of food now becomes an interesting issue. So the supply of food for species 1 is thus proportional to N2 of t, right? Because really how much food is determined by how much members the second species have. And their mortality rate is diminished when N2 of t increases. When I say there, obviously I'm talking about species 1. Okay, so the more is N2, the less death occurs for species 1. Okay, so let me try to write that down. So the first species death rate, remember that was a function of N1 and N2 in the general case. Now we are going to write this for this case. That's going to be a constant mortality rate, the same as before. But now it's going to be diminished by, with a parameter alpha 1, N2 of t. So there will be a constant mortality rate. But if there are more members of the second species, there will be more food. Therefore, there will be a reduction in the mortality rate for species 1. Okay? So that's one of the equations for this case. Now, what about the second species? Now, the second species obviously is drastically different. Mortality rate of species 2, on the other hand, to use this nice English expression, okay, increases when N1 of T increases. Why? Because that's the relationship, right? If there are more predators, you are being eaten at a faster rate, so your death rate increases. So for the second species, the prey, the relationship is, again, a constant death rate, but now you are being eaten more by this first species. So you have alpha 2 times N1 of T. And how much is determined by alpha 1 and alpha 2. So these are, again, two constant parameters of the model. So alpha 1, alpha 2, new model parameters. Okay. Remember system identification? If you ask how do I determine alpha 1 and alpha 2, system identification says, okay, you're gonna have some biological experiments with a certain types of species. You will observe them, collect data, and you will fit the model to the data, and that's gonna give you alpha 1 and alpha 2. Provided that this model actually is valid for that set of populations. Okay, so this is our two death rate equations. So I will again try to write the differential equations. Is there a question at this point? Okay, so we have d over dt n1 of t is equal to, again, lambda 1 n1 of t. Now minus gamma 1 minus alpha 1 n2 of t times n1 of t. Because we have now we have a new function for this death rate function. So we just insert that in our equation. So that gives us, if we expand that, we will have lambda 1 minus gamma 1 times n1 of t plus alpha 1 n1 of t n2 of t. Okay, and similarly d over dt n2 of t is equal to, again, lambda 2 and 2 of t minus gamma 2 plus alpha 2 and 1 of t. So that's the coupling between the two populations, and 2 of t. And that again expands to lambda 1 minus gamma 2 and 2 of t minus alpha 2
Lambda
times...
2 olmayacak.
Efendim? Evet, lambda 2 olacak. Şurayı düzeltelim. Bir saniye. Kötü oldu. Evet. Minus alpha 2 n1 of t and 2 of t. Okay? So that's our system now. Now this system behaves drastically different than the other system actually. So the question is how this new system behaves. Okay, we have to make some other assumptions as well. and I'm going to justify these assumptions. So we can further make the following assumptions. About our parameters now. About our parameters. Our parameters have to satisfy certain, what are our parameters? Lambda 1, lambda 2, gamma 1, gamma 2 parameters. Okay. So if there are no prey, if there are no prey, that means we have n2 is equal to 0. The predators cannot feed and their population will decrease. Okay, the predator cannot feed, and their population should or will decrease. So let's see what does that mean for the parameters. So if I have n2 is equal to 0, I should basically have dn1 of t over dt equal to dn1 of t over dt has to be negative. Okay, what was that equal to? That is equal to, remember, lambda 1 minus gamma 1 times n1 of t, right, plus 0 because of n2 being equal to 0, right? Because n2 is equal to 0. So that needs to be negative. It should be decreasing, okay? So because n1 is positive, right? So n1 is positive because it's a population. So that means I have lambda 1 minus gamma 1 has to be smaller than 0. Okay? So these two parameters have to have that relationship in order for the model to make sense. Okay? So when you are choosing lambda 1 and gamma 1, you have to be careful. They have to agree with this constraint. Okay? Similarly, we have if there are no predators, okay, the prey would multiply. That means for the case where n1 is equal to 0, yazdıklarım biraz geç geliyor. Duyabiliyor musunuz beni? Arkadaşlar beni duyabiliyor musunuz?
Duyabiliyorum hocam.
Evet.
Tamam, güzel.
Geç geliyor bana.
Okay. So in this case, right, if n1 is equal to 0, we need dn2 of t over dt has to be positive. Let's see what does that is that. Okay, dn2 of t over dt was equal to, right? So that's going to be lambda 2 minus gamma 2 n2 of t. But now the second term, right, the minus 0, because n1 of t is 0 now, okay? Because n1 is equal to 0. So this has to be a positive growth, right? The prey would be increasing in numbers. So because, again, n2 is positive, okay, so that means we have lambda 2 minus gamma 2 has to be positive in order for this to be satisfied. So that's another constraint on the parameters. Now let me show you, in order to finish, let me show you an example where we have some specific numbers again, it might be fun to play with this in MATLAB with different numbers to see what happens. Okay, so parameters that satisfy these constraints. So I will give you some numbers. Let's say lambda 1 is equal to 1, gamma 1 is equal to 2, lambda 2 is equal to 2, gamma 2 is equal to 1. These are arbitrary numbers except for the fact that they satisfy these two constraints. Alphas are 1. So what's going to happen is that you will have a cyclic behavior of the two species. Okay, so what will happen is that if this is time and populations, so what will happen is that now let's say that they both start at n1 of 0, n2 of 0 start at the same numbers. Now what will happen is that the predator will start feeding on the prey, so their population will start increasing. But at the same time, the prey, okay, because they are being eaten, they will start decreasing. Okay, so they will decrease. That's going to have a cap on, this is becoming tedious, but anyway, that eventually the population growth of the predator, so this is n1 of t, and this one is n2 of t. N2 of t. So this will be slowing down and will start decreasing because of the diminishing food. So eventually what's going to happen is that this will have a cyclic behavior, okay? And the other one will have a cyclic behavior with a phase difference, because you see, as the population of the prey decreases, at some point, these prey will start multiplying. So they will start increasing, okay? And then there will be another cyclic behavior like this. So these will be two cycles in a phase difference, okay? So there will be a kind of a phase difference here. It doesn't mean that the shapes of the two cycles will be exactly the same. They might be different, but there will be a sustained oscillation, okay? A sustained oscillation, behavior. Okay? So this apparently is very much in agreement with what is being observed in nature. Okay? So obviously that means for let's say if you're interested in some insect populations, you will have different parameters. If you're interested in let's say lions and deer, you will have different parameters, but this model can explain the cyclic behavior in nature of how these populations behave. Okay, these kinds of models are also very much used in economy, for example, modeling how people behave, how monetary systems behave, and so on. So it's a very good example on, let's say, a non-electrical example of how this modeling, process modeling can be used to develop mathematical models. Okay. Arkadaşlar 5 dakika geçirdik. Is there any questions, or you might go over it and ask your questions the next time as well? Okay. I'm here to answer any questions. People may leave if they are finished. Arkadaşlar teşekkürler. Yarın görüşmek üzere.
Hocam çıkmadı. Bir şey
Soru sormak
çıkmadı.
isteyenler sorabilirler.
Hocam ben ilk derse bayağı geç gelmiştim de hani yoklama bir tane alınıyor değil mi gün içerisinde? O yüzden ben yanlış yaptım. Hani yarım alınıyor değil mi yoklamadan yanlış cevap verilirse?
Şöyle hem geç gelip hem yanlış mı yaptınız?
Yok geç gelip yanlış yaptım. Hani yarım almak için ama bir nevi de yani mekanik yaptım. Ben de o mekanik yapanlardan biriydim.
Yani şöyle
O yüzden.
ben yani overall'da şu anda şey diye düşünüyorum. Bu arada soruda tekrar cevap verme şansınız vardı değil mi?
Bakmadım hocam. Yanlıştı. Bıraktım.
Bıraktınız. Orada normalde check diye bir buton çıkıyor mu altta? Çıkması
Diğer
lazım.
arkadaşlara sorabiliriz. Bilmiyorum ben de. Yani
Bir sorun.
Bak-
Yani normalde şunu yapıyorum ben. Hani soruyu kontrol edip hani bir penaltıyla tekrar cevaplama şansı verdiğimi düşünüyorum. Eğer mekanik olarak bir sıkıntı yoksa. Normalde bunu attendance gibi kabul ediyorum aslında. Yani
ben yarı yarıya diye
ortalamada
düşündüm de.
şöyle yani soruda eğer tamamen yanlış yaptıysanız 0 puan alıyorsunuz. Dolayısıyla hani bu yoklamayı kaçırmış gibi oluyorsunuz aslında. Yani bunun hani ne diyelim zaman içerisinde average out olacağını düşünüyorum.
Peki tamam hocam.
Ama yani hani sonuçta istiyorsanız hani tekrar açayım, girin, doğru yapın yani. Anlatabiliyor muyum? Çok kritik
Yok
değil.
hocam o zaman kalsın ya. Tamam teşekkür ederim.
Ya şöyle hani bir sıkıntı yaşarsanız gene söyleyin. Hani size bir çare bulalım yani. Anlatabiliyor muyum? Ama hani sonuçta şey gibi düşünüyorum. Çok basit sorular sorduğum için hani temelde işte dersi takip edip etmediğinizi hani o basit soruyla bir nevi kontrol ettiğimi düşünüyorum. Ama yani dediğim gibi hani bir şey farklı şeyler de düşünebiliriz.
Tamam hocam anladım. Teşekkür ederim.
Rica ederim. Dediğim gibi eğer attendance ile ilgili bir sorunuz olursa sonuçta bütün video kayıtlarımız var. Öyle değil mi? Dolayısıyla şey yapabiliriz. Yani dönem sonunda bir sıkıntı yaşarsanız geri gidip bakabiliriz attendance'larınıza. Çıktınız mı?
Hocam ben bir şey sorabilir miyim?
Tabii ki.
Mesela burada oscillation'ın damped olmamasının